Hello everyone, my name is Yamtanda Nyimbezi. Today we are going to present our task that we have done. This task was based on assessing the safety of the students from different residents to UCT campuses. So essentially we're just looking on how safe it is for students when they are traveling from their prospective residence to access different UCT campuses or library. So let's look on why this matters. This matters because well-being, accessibility, and academic participation for students can be easily disturbed when their safety is not taken into consideration. UCT reputation also can be damaged if the student's safety is not good, and by having a good safety for students, that can reduce the liability risk for both students and UCT. Inclusive access to education and community trust can be earned by ensuring that there is a well student safety taken into consideration. On this project, we focused on the UCT corridors, which is mainly Observatory to Claremont. This included side streets leading to UCT campuses, either driving or walking pathways. The data that we used for this project include bus or taxi stops, which had some attributes for it, like is it a shelter, is there any lightning, infrastructure rating, if is it good, shelter, poor, or just damaged. We also capture some security boards, their exact location, their operating hours, like is it 24 hours, 7, and if there is any CCTV present associated with it. We also had street light, which we checked if they're working, their brightness level, like is it good, bad, or is not working at all. We have also captured some hazards along the streets, which include vegetation that can be dangerous to students, like possibly maybe some snakes there, unsafe crossings. We also lastly used safe spaces. We looked for safe spaces like shops around, police stations, as mentioned again, 24/7 facilities like the security booths are around those routes that students use. So for this project, the analytical approach used include buffer analysis, road safety index, which is about qualitative scoring, hotspot mapping, which highlighted or shows clusters of unsafe or safe areas, or moderate areas of safety for students. Lastly, network analysis, which is about the safest routes computation. So this will be explained into details by one of my mates.
Hey everyone, Daniel Kimani here. I'm here to give a walkthrough and explain how we did our safety analysis for routes to campus, to the UCT campus. So in this analysis, we made use of infrastructural data such as safe spaces, hazards, and bus stops. So I'll first start by showing you our collected data and our area of interest. So our area of interest is this blue square here, which ranges from Rochester all the way to Claremont, with the UCT campus being over there. So the data we did collect was our safe spaces, which is shown by these purple crosses. We also collected our hazards, which is the red flags. We collected bus stops, which is the blue bus with the white background. We also collected street lights, which are streetlights, which were categorized into green for working and red for not working, and security booths, which is shown by the camera here, and our driving routes to the campus, to and from campus, which are in pink, and walkable routes, which are in purple. So from there, we went on to analyze the safety of each bus stop. So let me turn that on and turn this off. So each bus stop safety was color coded either using red, green, or yellow, in which these colors represent a risk score. So green being a risk score of 0, yellow being a risk score of 1, and red being a risk score of 2. So obviously, well, not obviously, but a risk score of 0 is the safest, and a risk score of 2 is the most unsafe. So let me delve into how we went into calculating our risk score. So our risk score was calculated based on the shelter, lighting, and rating scores. So if it had a 1 for shelter, which means there's shelter, 1 for lighting, which means there is lighting, and a good rating, then it got a risk score of 0. However, if more than 2 of the attributes, either shelter, lighting, or rating, were not good, then you got a risk score of 2. And if 1 was not okay, then you got a risk score of 1. And that's what led us to our color coding. So from our analysis, we do have 2 that are in need of service, and yeah, that's the conclusion that we can draw from this analysis. So next on, we went on to analyze our routes, or create buffers to analyze our routes. So the buffers we did create, we created a safe spaces buffer. Let me turn that on, supporting data. We created a safe spaces buffer, which had a buffer distance of 50 meters. 50 meters? Yes, 50 meters. We also had a security booths pavers buffer of 50 meters, and streetlights did have a buffer of 5 meters around each streetlight. These buffers were then combined into one layer, which we will call the safety buffer. This safety buffer, yeah, is just the combination of the different buffers, and then we went on to unionize them and dissolve the overlaps of these layers, which created this layer. Though color coded now, I'll get into how the color coding came about, but yes, this is the union output. From this union output, we were able to create indicator fields for each polygon, or each overlapping polygon, and these indicator fields were safe spaces, security booths, and light scores. So these 3 indicator fields, 1, 2, and 3, were then given different weightings. Safe spaces were given a weighting of 2, so we multiplied the score by 2. Security booths were given a weighting score of 3, so we multiplied the rating by 3. And light scores were given a weighting of 1, so we multiplied the score by 1. So when adding the 3 weighted values, we were able to come up with the safety index. So this safety index ranges from 0 all the way to 7. The lower the number, the higher the value, the more safety features overlapping, while 0 values show areas with limited coverage. After that, we ran a dissolve tool using the safety index field, to merge polygons with the same score, and that's how we came up with the color coding. This produced cleaner and larger safety zones, which we could then symbolize as, let me open that, green areas for safest areas, yellow areas for moderately safe areas, and red for low safety zones. Once our safety zones were ready, we then moved on to categorizing our routes, hotspot and thematic mapping. So using these buffers and our walkable and, let me turn these off, our walkable and drivable routes, we looked at how they intersect with these routes and what makes them safe or not safe. So let me turn this off, sorry for that. On our main routes, which these are our drivable routes, we had areas which are green, red or yellow. So let me turn off our buffers. So areas with green would represent areas of relative safety based off the safety index that we calculated. Red, the lowest safety, and our yellow areas are moderately safe. So these are on our driving routes. And then we went on to do our walkable routes too, of which our green is safe, yellow moderately safe, and red are areas that have low safety or not enough data. So then based off this analysis and our base data collected, we're able to make suggestions on what should be added or what should not be added. So we came to this 3 areas here. We do recommend that we should add security booths where the question marks are placed, because such bus stops do not carry any safety. As you can see, this whole area is red, this whole area is red, and this whole area is red. So that is our suggestion, that we should add security or better lighting in these areas. And thank you for coming to listen to my presentation and our presentation. And yeah, I hope that we're able to make these improvements. Thank you.
Everyone, my name is Bongusa Khumalo. I'll be taking you through the network analysis part of our presentation. The aim of this project was not only to simplify the network, but also to prioritize the safety for both drivers and we use ArcGIS to digitize routes, build network data set, and apply customized safety measures. By incorporating both driving and the walking networks, we ensure that our analysis could reflect how different groups of people actually moved. We started off with data preparation. The first step was data preparation. We digitized the driving routes, then walking routes was created as the combination of the roads of those segments on the driving routes that pedestrians are allowed to use, and combine them with the pathways that are within the study area. After this, we added a new field called safety scores to our attribute table. This field would later serve as the foundation for our safety-based routing. To calculate the safety scores, we looked at the hazard, safety spaces, security booths, street lights. We then assigned values as follows: 0.5 for safe roads, 0.5 for those roads that we deem safe or those that are closer to the safety spaces, and 1 for the neutral, 1 for those that are neutral, which are neither close to the hazardous hazards or safety spaces. Then 2 for hazardous roads, which are those that are closer to the hazards that we collected. This way, our network could understand the relative safety of each segment. Next, we created a network data set. By navigating to a database, under databases, we created a new database specifically for our network data set. And then under that database, we created a feature data set which we named safety routes and added all the layers that we are going to use for our network. Inside the network properties, we enabled the safety index under general. We enabled the safety index, which is this one, and then navigated to source setting and click group connectivity. Under policy, we change to any vertices. We change to any vertices because one of the most important thing here was to ensure the vertex creation when digitizing the roads, because without vertices, roads may look like they intersect on a map, but the network would not recognize them as connected. So by creating vertices at every intersection, we guarantee a proper connectivity across the network. We then created the travel attributes. Under travel attributes, we two travel attributes, the driving one and for the walking, and then the travel cost, making sure that the travel cost incorporates our safety scores that we created earlier in the attribute table. To make our network analysis more realistic, we added restrictions. For examples, car cannot travel against the direction of a one-way, and they are also excluded from pedestrian-only roads. Meanwhile, walking routes were restricted to pedestrians only. These rules made the network dataset more accurate. We then build the network by closing the properties field and right-click the network dataset and selected build here, this one. So after building the network, we then selected our layer that was created after building the network, and navigated to network dataset layer, then selected data. Under data, we went to network analysis. Under network analysis, we selected route, which is normally used to find the shortest path between stops. In our cases, we are finding the safest route. This highlights the paradigm shift from the normal route, which find the shortest or fastest route, to the safest route. Then selected this route. After selecting this route, we then have this layer, which is route. So after building our route and created the route under the network analysis tool, we then have to demonstrate how we'll now have to create few stops and see which route it would take. So to do that, we have to unselect other layers such as the main routes and only have this route layer selected. So to test our network, we have to navigate to edit and then create a stops. So to create the stops, you have to select stops. Let's say we are starting from here at Claremont. So the first point would be here at Claremont, then to UCT not stop. Then from UCT not stop, we'll go to, let's see, maybe here at GISc. So after adding the stops, what you have to do is to select network dataset layer, okay. To run the network, you have to come to, you have to select the network. You have to select the layer on the content, then choose route layer, then select run. Let's wait for it to run. So this is how our network analysis ran. It started from Claremont to UCT, then from UCT to GISc. Thank you.
Once again, so our findings show that security booths or CCTV are shown to be clustered near campus gates, and as you move away from the campus, there is few or less security booths or CCTV available. Street lights show some inconsistency, with several areas dim or street style are not working at all. Bus stops show poor shelters and inadequate lighting in many areas within our study area. With the hazards, the overgrown vegetation reduces the visibility and creates concealment risk for students, which makes them exposed to chances of being attacked by some animals that are dangerous like snakes. Broken and uneven pavements create trip hazards, forcing students or pedestrians to use routes that they may not like to use at some point. Side streets and campus approaches scored the lowest on safety index, meaning they are high unsafe areas. So our recommendation for short term are as follows. There should be installation of lights at dark bus stops and pathways. There should be repair of pavements and improve walkways. There should be cleaning of overgrown vegetation and provide shelters at high use transport stops. This obviously can be done by UCT in collaboration with the City of Cape Town for those that are within the main road streets. Our medium or long term recommendation are as follows. UCT must extend campus security patrols to high risk feeder routes. There should be a collaboration with the City of Cape Town as mentioned. There should be establishment of designated safety corridors routes from transport node to campus gates. There must be an integrated safety route index into all UCT future infrastructure project plannings. Thank you. This brings us to the end of the presentation. Once again, thank you for your time and listening to our presentation. Bye.